Hello, first period. So this is going to be. I'm only going to do the first part, and then I'll post the rest later. This is just if you get stuck up in class or if I'm gone for longer. Ooh, I hope not. So this is investigation 1. I forget what page this is on. Oopsie doopsie. But it started at the beginning of chapter 8. And so it's talking about the situation with mold. And you have X and Y. You've got this little graph. And then it says to calculate the PMCC, the R value. So remember that's from Pearson. So some of you that came up on our chapter 8 test. So just be mindful about if you see that name, like what they're asking. The first thing you need to understand, well, there's a lot, but is that these are the points that are graphed. And so I don't feel like that was clear, or maybe, I don't know. And again, this photocopy is a little bit bad, but you have one here, right? And we did this the Friday before break, but some of you were gone or I don't know. So you've got the situation. And so when you enter this into list 1, right, list 2, you can find your R value. Remember, if you go to catalog and turn diagnostic on, you have to push enter. It will give you your R value. I believe the R value is 0.961. I hope. And we're just talking about this data that's given to us so we can see the graph. And so because it's 0.96, that is a strong or very strong positive linear correlation. I don't know why I gave you more lines. I think I was just being careful. I don't know. But that, again, some of us were maybe forgetting this from our test, so just be ready for that. Okay, so that's just like a review. Setting up this thing. So it's like, okay, now give each data point a rank. And you're like, okay, I've never done that before. So you're going to order them largest to smallest or smallest to largest. It doesn't matter here. But we see that they started with H, right? So that's our largest. So I'm going to zoom in for a second. Hold on. Toot. So it tells you that right here. For example, H should be ranked, right? And again, it goes on to say, that it doesn't matter because the results are the same. And so just be consistent with that. Okay, so if H is 1, then my next highest point, if I think about the graph, is F. I gotta go back to my pen. I've got some wacky colors. Hold on. So F would be 2. And that's true for both my X and Y. Sometimes they don't match up. This table does, and that's a little bit annoying in my opinion, but they don't pay me the big bucks for no reason. So we already did H, right? We just did F. So then I'm looking at my table, or if you have a graph, sometimes you don't have a graph though, just saying. Right, I'm gonna see what's next. And it looks like A. So that for both is 3, 3. And then next is G. I guess I could zoom in. That wouldn't help my numbers. Ooh, that's a 4. Right, so I'm going down and putting them in order. So H was the largest, so that's number 1. F was the second largest, so 2. Third largest, fourth largest, so on. And I have the solution, so I'll save you the run around here. And they're equal. They're not always equal. So just don't think that they're always equal. Okay, so you've got this new situation, right? So you've got a table of the ranks. So this is the data. And then now you've ranked the data. So this is the ranked data down below. Okay, so from there, you're going to jump over to this little cute XY axis. And you're going to graph the ranks. And so, right, so I go from 1 to 8, right? So you can think about 8 being here. This would be 4, 4, 8, right? And it's a perfect linear line. Okay, so because of that, this R value is 1, right? Because it's like a perfect 1-to-1. And so it says calculate PMCC, so that's your R value. So again, you would enter the table. This would be like L1, this would be L2. You'd run your stats. And then it says comment on your results. So that is very strong. And I would say it's perfect, but you know, who am I? Perfect linear correlation. Oh, it's positive. Added positive correlation. Okay. Yeah? Ça va? So here I'm like talking about that, right? So I went here, and then I went down, and then I went over and out. Okay, so this is a new graph of our ranked data. It doesn't always look like this. It's not always perfectly 1. Sometimes it's decreasing. Sometimes it's like it's negative or it's positive, right? We don't know. The shape of the graph. So here, again, just to remind you, this little spider rock thing, it's definitely linear, and it is positive. I guess I have space to write it out. I didn't in real life, so you might not. Okay? All right, so this is the part we didn't get to. So this is the new thing. Spearman's rank. So it's just another dude, you know, living life, doing math, and he did something, so he gets a name, right? Everyone's a winner. So Spearman's rank is denoted R sub S. So this is how IB does the notation. I think I talk about this again later. So it's not anything except this like ranked R value. So if your Spearman's rank is 1, it's strictly increasing. If it's -1, it's strictly decreasing. And if it's... Oh, and this is, we'll actually come back to it later. It's called something else. If it's not, if it's something else, or if it's 0, rather, excuse me, it means that it's not consistently increasing or decreasing. Okay. Yeah. Generally, we'll look at data, I think, in these examples that are closer to 1, if I'm remembering correctly. Okay, I think that's everything from the first page. So again, on the next page, and in theory, you made your little booklets. We've got this big mess of thing. So you have a new experiment. So it's temperature, and then you have varied temperature is varied. The area of the petri dish. Okay, so you've got mold again now. So okay, so here's T. So I just want to bring that to your attention. And then here's your area, your mold. And then I'm gonna rank these two things. So I'm keeping these in mind, sort of like throughout this experiment, or this whatever. So again, in your calculator, I'm gonna zoom in. So this is just L1, right? When you enter an L2. So when I did this, I got negative 0.849. It's normally when we do this together, right? Maybe somebody like, oh, I got this instead. So if I made an error, please let me know. I also don't have the answer key to this because I'm here at home, and so anyway. And then again, what did I do on my key? So these again are like, I did it in the middle. A, B, C, D, E, F, G, right? So those are again descending. And because I have this negative 0.849, 0.85, right? This is a strong negative correlation. Period. Yeah, and like I could see that on my little scatter plot thing. Okay, so again, if for some reason I made a mistake, please let me know. I tried to do this. And this you would have just entered in your calculator. So I'm going to write that up here. Enter in calc. Okay. So when I rank them, it gives you 1 and 8 for H. So again, it's telling you that T is like the first, so it's the highest. And then your Y value is 8th, so it's the lowest. So this one's not going to match up. So I'm going to zoom in. Here's what I got. Again, if I made an error, please advise the class. 5 and 3, 6 and 5, 7 and 1. Oh. Hold on. 8 and 2, 7, 1. Oh, I missed 4, 4. Oops. Okay. See? Just kidding. E is 4, 4. 5, 3, 6, 5. Okay. So again, I would run the same calculations, right? L1, L2 in my calculator. For this one, I got negative 0.905. I believe that's correct. You think so? Well, okay. So this one's negative, and it's asking you what the features of the data that led to this, like the Spearman rank value. And so one thing that happens on our graph that we can see, right? So as T increases, Y is decreasing. And so I have something that is like going to the negative. Does that make sense? Like it's decreasing. Yeah. B sort of changes that. So it's not strictly decreasing because that B sort of like bounces up. But it's headed that direction. So I'm going to write something about that here. As T increases, Y decreases. And again, this would be like a strong negative, correlation. Okay. One thing, and I know this kind of jumps around a bit, but this is why we have color. So it's like over here, the PMCCC. So the Pearson moment correlation coefficient thing, whatever it's called. Right. So like we're finding of the rank. That is this calculation right here. Like that's what we're doing when we're finding that new R value. So the PMCC of the rank values of the data is called Spearman's rank correlation coefficient. Sometimes I swap the C's in my mind, so I'm sorry if I coefficient. Okay. And then sometimes you will see it like shorthand, right? Because like we have all these like acronyms. So like again, the Spearman's rank shows the extent to which one variable increases or decreases. But the other one is still increasing, if that makes sense. Yeah. Okay. And again, for this, the notation is R sub S. Okay, monotonic. So this means, and this one I'm still like wrapping my head around, so come with me on this journey. So this word is data that is only, I'm going to go over here because I write big, increasing or only decreasing is known as monotonic. Okay, so another thing, so like when we have R sub S equals to -1. This is monatomic, for example. Okay, zoom out. Okay, we have these two examples and then the advantages. So again, it's a little bit hard to see, and these are examples from your book so that you have the answers. But when you put them into your, right, so again, L1, L2, first you have to rank them. Sorry. First rank. Then calc. So I got -0.956. For the pets and time spent each week, I got positive. Yeah. Okay. So, yeah. Check your numbers. And again, those should be in the book. I forget what page. I'm sorry about that. All right. So over here, why do we care? Why do we do this? Well, because we can. Just kidding. I'm going to zoom in so I can write better. So the advantages of using Spearman's versus just the regular R value when it's not ranked is you can use it on data that's nonlinear. Used on, I'm going to say nonlinear data. Yeah, so maybe something in the real world is nonlinear. That would be helpful. It can be used on data that has been ranked even if the original data is unknown, which is helpful if you don't know your original data set, which sometimes we don't. So it can be used on data that has been ranked even if the original data is unknown. Okay, last one. It is not as affected by outliers as Pearson's. So again, talking about our sub S, it is not greatly affected by outliers. Okay. Yeah? Ça va? Okay. Next. Chi-squared test for independence. Hashtag free Britney. Okay. So this big X is not X, it's chi. So what am I gonna do? I'm gonna write this over here. Is chi. Sounds like, I don't know, chi, like that with a K. It's a Greek letter. So the big, and this one's a little bit long, so I don't think you're going to get through this. Oh, I'm looking at my key here. I don't know what you're going to get through, I'm sorry. But it's all about hypothesis testing, and that's like where we are able to do our statistical inference. So this is like the whole sort of like shebang of it. So, and this bubble got cut off, and I'm so sorry about that. I feel bad. Okay. And then the investigation, I'm going to let y'all try that on your own. I might give you a little hint. Or no. I'm going to let y'all do that on your own, but I'll post the key to it. Just because I want you to be thinking. Okay, so first bubble, hypothesis testing in stats. Let me get a good color. So in stats, hippopotam. Hypothesis is a statement about the unknown parameters, like the things you are measuring. or features of a data set. Okay, so like you're going to say something and you have to sort of like prove if it's true. So the aim of a statistical test is to try to find out whether the data supports your hypothesis. It's like science class, but different. Or maybe not. I don't really know. Blue. Okay. If it does, this is an example of statistical inference. Statistical inference. Inference. Are there two R's in statistical inference? Oh god. Inference. Hold on. I don't feel like that. That doesn't look right. Okay, well, you get back to me. Because inferred has two R's. Okay, I'm sorry. This is not the point of this little bubble here. Okay, if it does, this is an example of statistical inference, right? Like you are finding the thing. You have inferred something from the stats. Yeah? So like you've learned something. Okay. Number 1, our initial hypothesis is called the null hypothesis. You will have never written hypothesis as many times as you have now. This gets H sub 0 or sub naught, sometimes people say. It's a little 0. Every hypothesis has an alternate reality. No, just kidding. Alternate. Oh no, it's alternative. Sorry. Alternative hypothesis. It's that IB lingo. So, right, like it's cloudy today or it's sunny. So if it's sunny, then it's not cloudy. So the alternative hypothesis will be accepted if the null hypothesis is rejected. I'm going to do that in orange. Wah. Okay. And this is written as H sub 1. Yeah? Okay. Sweet. So you're going to do the investigation. It's about a coin. Surprise, surprise. And you're tossing it 10 times. So it's your trial size. Yeah. And it's talking about fair coin. So without any calculations, so you do not need calculations, use the logic, write down a range of values for the number of heads to appear in 10 tosses. They'll make you reject the null hypothesis, right? So if I have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They can't all, right? Like, it can't all be tails. They can't all be heads, right? So you're going to come up with a value that would mean that it's fair or not fair. Or reject, yeah. Okay, ça va? And then you're going to use the binomial distribution. So that's in your calculator to work out the probability of events listed in 1A. So that's from above. And then do you feel that the probability is small enough that you could reject, right? So if you're like, well, actually that's a pretty good chance, I would accept. So you're going to have to come up with that for yourself. And then down here, it talks about, kind of helps you out here. So explain why you would choose your null hypothesis to be, right? The probability is 0.5 for flipping of a coin. Yeah. So you're going to do that. You are going to do that. You do. Okay. So that. Next. Okay, welcome back, because you just went and did that other thing, right? This page, I'm still not sure about. On my key that I have at home, I wrote a bunch of stuff, but I feel like I repeated myself, so I'm gonna skip some of that. But there are 2 exam hints, so highlight, please. Thank you. And again, before you take your exam, for those who are examining, I would like go through the book and just like put these somewhere. So it tells you, right, you'll only be 1%, 5%, or 10%. And then it tells you how to do it, like how to like do the matrix operation on your calculator. Because you will do it on the calculator. Calc. So this is like calc. Okay. Anyway, so events. So from part 1A, which you already did. Oh, this is gonna give it away. Okay. That's fine. Okay. I'm going to come back to that. I'm going to let you were going to say that. Sorry, that took me a second. But this is just the significance level that you're using. And so it like, you continue. This is the investigation. So you would like go through this. I will tell you this though. I'm going to zoom in, sorry. So the conceptual, so what is meant by the significance level of a hypothesis test? So this is like the size of the confidence interval. Because it's going to be a distribution. You know it is. It's like the certainty. Yeah? Certainty. Okay, spelling is off today. Sorry. And then number 7, what is the purpose? Okay, calm down. So this is like how we draw the inferences. We draw the inferences. I think it's just one over there. On our data. Like that's why. Okay. One thing I do want to say, so you're going to do that. You're going to say if it's accepted or rejected, basically. So I'm going to let you do that. I want to say that, okay. We're going to talk about degrees of freedom next, but I want to say that there's a few things I want to say. Okay, so chi-squared can be used to test whether two variables are related or independent from one another. Okay. The next thing I want to say, I'm going to zoom in for a second. It depends on the size difference, like the difference between what you observed and what's actually going on, the degrees of freedom and the sample size, but we're going to talk more about that. So, maybe that's all I want to say right now. I'm just going to leave it at that. There's a bunch I could say, but I'm going to leave it. Sorry. Okay. This is where I'm thinking that you will get to is this coffee example. So if not, that's okay. We'll do it next time. So you've got this, and this is from the book, so you could check in the back of the book. It's like a example problem. Max was watching people coming out of a takeaway coffee shop. He was assuming their gender and whether they bought a small, medium, large coffee. So again, we have the gender binary, and I'm sorry, but I'm not surprised at this point. First thing I want to fix is this down here. So F0 is, I think I had equal signs, but this is your observed F sub E is your expected. That one I could see better. I think I had like little equal signs. Okay, sorry about that. All right, so you've got these different sizes, and so you have a total, right? So you have all these totals. So your grand total of 110 is going to be important later. So just remember that. Thank you. And then your totals for your men. And then I did yellow on my other notes. I'm going to try to match those. My ladies. And then you have like a medium totals. You have small totals. And then you have, I need large. Your large totals. So my totals are where I'm like how I'm going to do my calculations. That's why I'm highlighting them. One thing I'm not sure about this page, because I made this before break, so anything is possible, is the flow of it. So one thing that this is assuming is that you don't yet know the like calculation, or maybe you are supposed to know the calculation, but we're going to kind of just do it all together, and I'm sorry. Okay, so in the table of expected frequencies, so that's what we have here, expected frequencies, the totals of the rows and columns are fixed to match gender and coffee size. So those are fixed, so that's important. When completing the table, so imagine that you would have to do this, you probably are going to in the future, you have some number V, which is called the, it's not very exciting, degrees of freedom. Yeah? Okay, sweat. There's a formula for this, so hang tight. I'm going to zoom in because I'm going to write small. So V, the degrees of freedom, are the rows minus 1, do an American one for y'all, times the columns minus 1. One thing. Do we include the totals? No, we do not. Not including totals. In exams, V is always greater than 1. That should make a little bit of sense. But okay, so we're going to do that in a second. Okay, so let's go back up here. So the question is asking, you're like, there's so many things I can do with this table. Show that the expected number of males who buy a small coffee is 16.7. So we know that. We like the expected numbers should be this. We've observed something, right? These are observations. These are observed. So now I'm talking about the expected. So again, we're going to talk about this later, here in a second. But I'm just going to see, I just don't know why I did it this way, but that's okay. They're proportional. So we're going to do that. So here's my little table. So again, I want to prove that the expected numbers for men, small coffee, so I'm talking about 12, right? The expected is actually 16.7, so it's higher than what I observed. Just saying. So, men, small coffee. I've got 54. But that's out of my total, out of 110. Okay. But the small coffees, right? So I had a total of 34 small coffees. Right? So the probability of getting small coffee out of the total is this, whatever this little decimal would be, out of 110. And then I need to factor in that there is a total here. So there's 110 that I'd be multiplying by. So you're going to run this in your calculator. One thing real quick, I'm going to use a little highlighter here, right? One of those will cancel. So if that helps, so be it. So when you calculate this all out, you in fact get 16.7. It's magic. So again, I'm finding the probability. Should I do that? This is the probability of small. This is the probability of a male. Or I'm going to do... I'll just write it. And then this is the total, right? Total. Okay. Yeah? That looks like mole, but I mean... And then it's asking the difference between observed and expected. So that would be 12, take away 16.7, which is negative 4.7. That's important later. Why is it 12? Because it was 12 here. Oops. In my table. 12. Okay. Okay. There's a reason for this. It's not clear yet. And maybe it's because I haven't had coffee because it's almost 9:30 p.m. Okay, so show that the expected number of females, so ladies, large coffee, is so it's like supposed to equal 23.4. So again, I need a different color pen. So I would have, it's 23, yeah. So I would have 56 out of my 110. So that's the probability of a female. And it's a large coffee, so that's my pink pen. So large was 40 out of, 46. So 46 out of my total, 110, times my total of 110. Again, one of those is going to cancel, so you're left with 23.4. Okay, so again, the females who buy a large coffee, that one was 18. Yeah, sorry, 18. Right, so I was here. So over here, the difference, so I would have 18 minus 23.4, which is, I believe, negative 5.4. They're negative, that's okay. It's fine. It's totally fine. Okay, so what we're gonna do next, so if you were like in the book, so that's A, B, C, then it's like find chi-square value, and you're like, whoa, I don't know how to do that. You do. You truly do. You really do. And so can you imagine that, oh, my battery's low, that you would enter this into a matrix and then you would be able to run your calculation. Yeah? So you're not going to do this by hand, hopefully. If it's small enough, you could, but. Okay, so in order to make sure the differences are in proportion, that's the word that goes there, proportion, it's better to divide each difference squared by the expected value. This calculation will give you the chi-square statistics. Yay! Okay, so again, this is where I still get a little bit confuzzled, and that's fine. I'm human, you know. So for this coffee, right, coffee gender, my null hypothesis, I believe. So again, if you have one that's better, please let me know. But my null hypothesis would be that coffee size doesn't matter. Sorry, is independent of gender. Because it should be, right? Right? That's an N. So if that's not true, so my alternative, let's get orange, I don't know. So if that's not true, then I would say, you could say it a couple different ways. And again, you can get a whole degree in statistics and just really go for it. So I wrote this, I said this, coffee size is not independent. Independent. You could write dependent, but I feel like it has a different connotation of gender. Right? Like I could infer that it was dependent. You know? I don't know. Okay, so the other thing we need to care about is our degrees of freedom. Right, so I only have small, medium, large. I don't have like an Ice Fente I don't have a short, I used to work at Starbucks, right? There's lots of different sizes, so I only have small, medium, large, and I have the gender binary. So my degrees of freedom, again, remember that's that rows minus 1. So for my rows, I have 2 minus 1, so that's my gender. And then I'm timesing that by my columns minus 1, minus 1, oh God, which is 3 minus 1. So that was my coffee size. Okay. V equals 1 times 2, 2. So I have 2 degrees of freedom. That's important because that will tell us something in a bit. So again, you're going to have this equation. So again, the summation of your observed, take away your expected, that thing squared divided by the expected. So again, this, I'm going to like draw a star here because it's the star here also. It kind of like explains it. I'm going to fill that in because that turned out to, well, it's still pretty ugly. The other thing here that got cut off, and I'm so sorry, and I know this video is super long, but this is what you get. So if, you see how it should be if the number is greater than the critical value is related to your degrees of freedom. Value rejects your null hypothesis. Period. If, and I didn't do that, I'm sorry. Let's do like a lightning bolt. If the number is less than your critical value, accept your null hypothesis. So that you would have done in your investigation, n'est-ce pas? Okay, so coffee, right? So we did this, observed versus expected. So coffee still. Oops. So it wants us to find chi-squared. You're like, okay, cool. I'm going to just like run the calcs, run it back. So hold on. Let's figure out how this works. Sorry, I had to move. Okay, so I did the gender symbols. I hope that's not problematic. I know gender is a construct. I know. I'm sorry. Okay, so when you calculate everything, and I have like a very rough table that I'm going to like give you a picture of because I don't want to rewrite it. But female small, 17.3. For medium, 15.3. For large, 23.4. And it's also like, can you have, 0.4 of a person? Maybe. I don't know. So here are the values. Lots of larges, eh? I get it though. Okay, so you have your expected. So in order to find chi-square, we have to sort of, well, we don't have to, but we're going to do this little table. So we're going to like show how it works. So you have your observed. The 16's out of order because I forgot it, and that's how life goes. So I'm sorry about that. But the expected, so for 12, and again, like you're referencing your previous table. So maybe I'll write that, reference previous table. Okay. So 16.7, 14.7, 23, 23.4, 22. Some of the numbers will be the same, which is really nice. Some of them are 4 decimals. I don't know why. I just work here. Okay. Yeah. So let me change colors. And then let's do green. It doesn't really matter. So when I subtract them, so that was a positive difference. This one's negative. Negative 5.4. Positive 5.4. I don't know if your real data will be this nice. If I had to guess, probably not. So then I'm going to square them. Why would I square them? 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 Why would I square the difference? I don't know. Think about it. So this one's 4 decimals, and I don't know why. I'm just, again, reporting the facts. Some of these are the same. 0.49. Okay. Orange. So now I'm going to divide by the expected. So again, remember that f sub e is expected. F sub o is observed. Okay. Oh, I have space to do my French ones. So again, 0.033, 1.25, 1.29. So you had to round these. There was some rounding errors. We're going to have to just work on that more and more and more. Okay. So remember that the equation is, well, actually here, I'll write it for you real quick. I don't know. I'll write it here. So your chi-squared is your sum of your observed minus your expected squared divided by your expected. So you're going to add them up, sum. So you're going to add up this column. So chi-squared, and again, I got 2 different values, which I'm surprised at. But when I did it, and I checked it, and I checked it, and I checked it, I got 5.205, which I then rounded to 5.21, 3 sig figs, if you will. So, for 2 degrees of freedom, because remember, like, it matters that I only have small, medium, large, and then the gender binary. So for 2 degrees of freedom, my chi-squared at a 5% significance level is 5.991. Okay, so, and here again, if I misspeak, it's going to be right here. Since chi-squared is less than chi-squared at my 5% significance level, so again, that's, I've got 5.21 is less than 5.991. We would accept the null hypothesis, which was that gender and coffee sizes are not related. I think. I'm like pretty sure. My confidence is small interval, actually. Okay. So last thing here, you've got this little box. There's different ways to write it. So our book uses this. Real life. So here, I'll use this book. Real life. So usually the p-value is what you'll see in like research papers. So if you're doing this sort of thing for your IA, I would resort to that. Just saying. Okay, so that is it. For now, if you have time, do this. I don't think you will, and I'll add that to the notes. And then I'll do this anyway, but I don't want to, Okay. Oh, and then a calculator. T-test is just a calculator test. Don't overthink it. I love you. Same thing. Okay, bye.